Lesson 1.4 Atomic Theory. Um, the first thing we're going to talk about is the nature of the atom. What are atoms made up of? The first proposal was made by Democritus back in 460 BC, where Democritus said, okay, matter is made up of a bunch of tiny individual particles called atomos. These particles cannot be further divided. They're uncuttable. You cannot have one fourth of an atom. You cannot have half an atom. It must exist as a one. That's what he said, and we later called these particles atoms. John Dalton came up with the atomic theory. Very, very, very popular, and you should familiarize yourself with it. Um, so at this point in time, atoms were known to be very just particles. We don't know anything else about them. We're not even close to this idea of the atom yet. Um, John Dalton proposed four things. You should know them really well. Each element has many identical particles called atoms. So, for example, the hydrogen in water is the same as the hydrogen in hydrogen gas or hydrogen peroxide. The hydrogens are atoms and they're all the same. That's what he said. Okay, so whether the hydrogen comes from water or hydrogen peroxide, the hydrogen is an element, but they're all identical atoms. So people use the word element and atoms interchangeably, and that's fine. You can use them interchangeably. Um, Now, two, this one's a little tricky. John Dalton said all atoms of the same element are identical. So carbons are identical. Okay? And it's true, they're identical um because they have the same number of protons and they have the same number of electrons, but there are different versions of atoms, and different versions of an atom or different versions of an element are called isotopes. Okay, for example, there's carbon 11, carbon 12, carbon 10, and those numbers represent the mass of the carbon. So, in reality, not all atoms of the same element are identical, but I think what they're trying to say is that um, their properties are extremely similar, their structures are extremely similar. So at that time, they thought that all atoms were the same. Okay. So we could think of them as similar, not the same, because of the isotopes. Isotopes are the same element, so carbon, they're all carbons, but they have different number of neutrons. And because they have a different number of neutrons, they're called isotopes. And because they have different number of neutrons, they have a mass that is different. For example, carbon has 11 atomic mass units, while another carbon is going to have 12 atomic mass units. And we'll talk a little bit more about that. The third um, rule that he came up with is that in a given compound, the amount of atoms are identical. So, for example, C6H12O6, you learned that in your biology class. You know that it's glucose, and what it's saying is that in a given compound, the amount of atoms are identical. So, um, for example, glucose could exist as C12H24O12, and it's the same thing as saying C6H12O6. It's just reduced. And so you could use proportions to figure out um, how many atoms you have in a given compound. And we'll talk a little bit more about that. If that's a little bit confusing, it can be, but it'll make more sense later on. 4, the total mass of materials after a reaction is the same as the total mass before the reaction because atoms cannot be created or destroyed. So this is the first law of thermodynamics. The first law is the law of conservation of mass. So the first law says that the mass in the universe is conserved, that the energy is conserved in the universe. And you learned a little bit about this when you did the tasks, when you applied for AP Chem. But basically, you do a chemical reaction, you have a closed system, a system where no matter is allowed to leave the system. Um, and if you measure the mass before and after the reaction, it should be the same. It should be the same. But if you leave the system open, for example, if you have a chamber and you expose it to the air, then the mass could go up because some of the matter might absorb or take in some of the oxygen in the air. So when you calculate the mass at the end, it might be higher, or some of the matter might evaporate, and so the matter might be less once the reaction was completed. So the question in red says, but what if a reaction occurs in an open container and the mass is less? That's because some of it escaped or some of it was transformed into some other form. It was transformed into vapor, it was transformed into energy, or was transformed into heat. All those things could happen in a chemical reaction. So we talked a little bit about this. Which law is it? If water, the structure of water is down here. If water has oxygen, one oxygen with a mass of 16 grams, then H2O2 would have 32 grams from oxygen. So what law supports this theory or this idea or this claim? And it's the law of multiple proportions, right? So if you have one oxygen, it's 16. If you have two, then it should be 32, right? And because there are different isotopes of oxygen, it might not be exactly 32. It might be 32.2 or 31.9, something like that. So it says, the PowerPoint says, this water molecule, is it a space-filled model or a bond-stick model? And you should know that it is a ball-and-stick model, right? Because it has the stick and it has the balls. So the stick is the bond, the ball is the atom. So there's one red one, so that has to be oxygen. It's bigger in size. Hydrogen is smaller in size, and it has two of them. And then at the bottom it says the structural formula. So it's H2O, right? Um, it the oxygen is connected to two hydrogens. And then on the right, it's asking for, is it cis or trans isomer? So this is H2O2. You don't see the isomer here in this PowerPoint, right? You don't see it. If you just flip it around, it's considered an isomer. But since it's symmetrical, if you draw a line straight through it, it's symmetrical. But so you might be tempted to say that it's cis, but from the last lesson, I'm actually not sure we went over it, but do you see this little dash here, this dark dash here? That means that the bond is moving towards us. Okay, it's moving through the page, through us. And the one on the right shows a dashed line, and that means that it is into the page, into the screen. So they're pointing at different orientations. So if they're not pointing in the same orientation, then it's considered trans and not cis. Okay, so it's trans because the bonds are not in a three-dimensional space. It is not moving in the same direction. They're actually moving in opposite directions, making it a trans isomer. Okay, even though the isomer is not drawn in this picture. Okay, the next scientist that I want you to know about is J.J. Thomson. It's a very simple experiment that he created. He's the guy that's responsible for discovering the electron. Um, so J.J. Thomson, what he did is he had this tube right here that generated a voltage, and what he did was that he created this cathode ray tube where streams of rays were shot through the tube, and these negative charged particles were shot across it into a plate. Okay, this positively charged plate. It turned out that the negative charges from the cathode ray were attracted to the positive plate. So this showed us that the electron had a negative charge, or these particles had a negative charge, and they were called electrons. So, um, so this proved that opposite charges attract, and then two, that electrons are negatively charged. So he discovered the electron. Um, so there's a quick write that says, based on model 1, which is this model, what can you conclude from the results? So this was actually supposed to be a quick write before I actually just told you what I told you. That negatively charged particles are attracted to the positive plate, meaning that the electron has a negative charge, and that opposite charges attract. That's what they got out of it. And if you notice, you could also come up with something based on the negative plate, that negative charges repel. That is very important to know. Negative charges repel, whether it comes from an electron, whether it comes from a negatively charged plate, it will repel. Okay, and model 2, what could you conclude from model 2? I recommend that you pause this right now and think about it. What can you conclude from the results of model 2? So go ahead and pause it, think about it for a moment, jot down your thoughts, and then I'll explain it. Okay, now that you have time to think about it, so it is a very, very, very similar device that was used in Model 2. Lead block, radioactive substance was shot through a hole, and then you have a positively charged plate and negatively charged plate, and you notice three different rays appear on the photographic plate. So the first one is the beta rays. So you're shooting radioactivity through there, and the radioactivity comes in three different forms: the alpha rays, the beta rays, and the gamma rays. Okay, however, they're very different. So because the beta rays were attracted to the positive charge, that tells us that beta rays are negative. And the reason why is because beta rays have negative charge, negative electrons on them. Um, if you shoot something, a radioactive substance, through and nothing happens in the presence of the charged plates, then you know that it's a neutral substance. So gamma rays are actually neutral. And if you shoot the alpha rays through there, and um, they attract the negative charges, then you know that alpha rays have positive charges in them because they attracted the negative plate and repelled the positive plate. So you could conclude that beta particles have negative charge, or negative charge. And the gamma rays, in purple here, these are gamma, they have no charge because they were not attracted to the plates, while alpha particles down here were attracted to the negative plate, meaning that the alpha particles, the alpha rays, have a positive charge in them, and they repel the positive plate too. So that's what ended up happening. The last PowerPoint slide I want to go over for this part of the lesson is J.J. Thomson's um, other proposal was that he took Democritus' idea that atoms are particles, like this one, and he said that because of these rays, we know that the particles inside atoms have charges, and he said, I think the positive and negative charges are found in an atom, and they're evenly distributed inside the atom, like the raisins found in pudding. So that's why it was called the plum pudding model, because they were evenly distributed just like raisins were in pudding.